We are in section 6.2, differential equations with growth and decay. So we need to solve the differential equation y prime equals 2x over y. The first thing to do when you're trying to solve a differential equation is turn the y prime into dy dx, because what we're going to do now is something that we call separation of variables, and that's getting the y by the dy and that dx by the dx so that we can integrate. That's the only way to solve a differential equation. So we're essentially going to be cross multiplying. So we'll have y dy equals 2x dx, and then we can take the integral of both sides. The integral of y is y squared over 2, and the integral of 2x is x squared. We have to have a plus c. Now, it's okay to just have one c because a constant plus a constant is still a constant. So even if you put a c on both sides, it would be all right to switch it over to one side. Okay, and that's okay right there. Otherwise, you can solve it for c if you'd like, but that's fine with me. Okay, this is a model that you're going to have to know and know how to use. It's CE to the KT, where C is the initial value, K is the proportionality constant, T is time in years generally. It's very similar to PERT, so if you can't remember CE to the KT, just try to remember PERT, where K is the same as the rate and C is the same as the principal. The rate of change of Y is proportional to Y. When T is 0, Y is 2. When T is 2, Y is 4. What is the value of Y when T is 3? So if this is true, because C corresponds to the initial value, we can go ahead already and say, okay, then C is 2. And then we're going to use this other fact, when T is 2, Y is 4, to figure out what the K is. So if we have Y equals 2e to the KT, we're going to put in 4 for Y and 2 for T, and then we're going to solve for K. So we're going to divide. We're going to have to take the natural log of both sides to get rid of the e. So K is the natural log of 2 over 2, which is approximately 0.3466. Going to 4 decimal places is the best for these. So our function is y equals 2e to the 0.3466t. What is the value of y when t is 3? So put 3 in for t. Y is approximately 5.657. Here's the half-life of a bunch of different isotopes, and this would be given to you in a problem, but this is just something for you to use for your homework. If we have 10 grams of plutonium and it was released in the Chernobyl nuclear incident, how long will it take for the 10 grams to decay into 1 gram? So if we start with 10 grams, that's your C. So we already have y equals 10 e to the KT. And then we know half-life of plutonium is 24,100 years. So we're going to use that fact to figure out what T is, or K, I'm sorry. The K is the constant is always the hardest thing to find. So if it's 24,100 years, then our Y would be half of what it is now, so it would be 5 in 24,100 years. The natural log both sides, just times K. K is equal to the natural log of 1/2 divided by 24,100. If you divide that out, K is approximately negative 0.0002876. So if there's a bunch of zeros like that, you're obviously not going to just go to 4 decimal places. Go to 4 numbers. So if it's all zeros and then 4 numbers, you can stop there. So our function is y equals 10e to the negative 0.00002876 t. And then the question is, how long will it take the plutonium to decay into 1 gram? So that's our y, and we'd have to solve it for t. Okay, so 1/10 equals e to to negative 0.00002876 t. Take the natural log of both sides to get the e out of the way. And t is natural log of 1/10 divided by negative 0.00002876. T is about 80,059 years. So there was really no calculus involved in that. It's just problem solving with the decay function. Next one, we have experimental population of fruit flies. It increases according to the law of exponential growth. There were 100 after the second day and 300 on the fourth day. How many were there in the original? So we have two different functions here. We have 100 equals CE to the 2K because it took 2 days. And then we have 300 equals CE to the 4K. So what we're going to do is solve both of these equations for C. If I divide by e to the 2k, that becomes e to the negative 2k on the other side. And then if I divide by e to the 4k, it becomes negative 4k on the other side. And then I have both of these equations set equal to c right now. So I can set them equal to each other. This will help us solve for k. So I want to get both of those on the same side. So if I divide by e to the negative 4k, then that would be e to the positive 4k. Multiplied by e to the negative 2k is e to the positive 2k. Divide by 300 or 100, you get 3. Natural log both sides. K is approximately 0.5493. Then we're trying to find what that initial population is. We can use either one of these. I'm going to go with 100 after 2 days to find the C. So you can just do 100 divided by e to the 0.5493 times 2, and you'll get 33 flies in your original population. Four months after it stopped advertising, a manufacturing company notices that its sales have dropped from 100,000 to 80,000. If the sales follows an exponential pattern of decline, what will they be after another 2 months? We're going to use t in months. If all of your data is in months, you can use any other, you can use that for your t instead of years. So we have y is 80,000, t is 4, and this initial is your c. So now we have, if we want to find what the k is, we can put in 80,000 for y, 100,000 for c, and 4 for t. So 0.8 equals e to the 4k. Take the natural log of both sides. K equals natural log of 8/10 divided by 4, which is negative 0.0558. What will the sales be after another 2 months? So another 2 months is when t is 6. So we're going to put 6 in for t to find our y. Type that straight in. About 71,500 units. Okay, then we have one more problem. This is on Newton's law of cooling. So Newton's law of cooling is that y prime is equal to k times y minus Tc, where Tc is the constant temperature. Okay. So if we start at a constant of 60 degrees, y prime, of course, is dy dx equals k times y minus 60. And we're going to do separation of variables here. dy over y minus 60 equals k dx. Take the integral both sides. Instead of, go back a little bit, instead of doing x's, we're going to do t's. So we're in terms of time. Okay, take the integral. Right side, it's natural log, absolute value of y minus 60 equals kt plus c. And exponentiate both sides. So y minus 60 equals e to kt plus c. And our temperature function will be y equals 60 plus c e to the kt. I can pull that constant out because I'm doing the inverse of the exponent rules. If you have addition, you can change it to a number out front, e to the c. This is going to be e to the c. But it's still just a constant, so we can just call it c instead of e to the c. So now we have two different conditions. We have the temperature, the initial temperature is 100, and then in 10 minutes it changes to 90. Then we can say already that we know what the c is. We have to find the c. So 100 equals 60 plus c to the e to the 0 if time was 0. So it's not just going to be the c like it was in our other functions because we have that 60 out front, but the c here is 40. Now we need to figure out what the k is. We're going to use our other condition that it was 90 degrees in 10 minutes. 90 equals 60 plus 40 e to the k times 10. 3/4, that's from subtracting the 60 and dividing by 40, you'll get 3/4 equals e to the 10k. Make the natural log of both sides. K is equal to the natural log of 3/4 divided by 10, which is negative 0.02877. So our function is 60 plus 40 e to the negative 0.02877 t. How much longer will it take for the temperature to decrease to 80 degrees? So now we put in 80 for y and solve it for t. Subtract the 60, divide by 40. That would be 1/2. Get rid of the e. T equals natural log of 1/2 divided by negative 0.02877. There's 24.09 here in terms of minutes. Okay, and that was the last part of section 2 in chapter 6.